What I'm going to do is I'm going to take this concept with this airfoil based on this number. I'm going to explain to you why that looks like that. And then I'm going to carve it all into a block of wood, and it's going to come out looking like this. So this is from design process to product, NACA Airfoils. Here is a teardrop. This is the most aerodynamic shape possible. The air hits the curved front edge and is gently guided along, where it re-meets the other air at the back due to the tail being kind of pointed. Now, an airfoil does a similar thing, but is shaped slightly differently. This is shaped like this in order to create a lower pressure zone up here by speeding up the air on the top, and a higher pressure zone at the bottom by slowing down the air. If we then take that airfoil and give it a positive angle of attack by angling it upwards, what we can do is have some of this air come and hit the bottom of the airfoil, sending it downwards, but also slowing it down even further. This creates an even higher pressure zone at the bottom, but a relatively low pressure zone at the top, creating an upward force, also known as lift. These are the basic principles of an aircraft wing. The reverse is true for a wing on a car that is meant to create a downward force, also known as downforce. NACA numbers are how we define airfoils. Using these 4 numbers, we can decode exactly what the airfoil looks like using some clever equations. First number, 4, is the maximum camber. This is where the camber line is at its greatest distance from the chord line. This says 4, and it is in hundredths of the chord length, which is very important. It's the distance from the leading edge to the trailing edge of the airfoil. So from this, we can calculate maximum camber to be 0.2. Our second number, 4, is the location of the max camber. So at what point along the chord line is the maximum camber at? And this number is in tenths of the chord length. So we multiply the chord length times 0.4, and we get 2. So we know that the distance from here to here is 2. Finally, we have the maximum thickness of the airfoil, which is right here. And this is a 2-digit number, and that is in hundredths. All of this math that I did right here to decode this number, we will do in MATLAB, because there's really no point in us doing it ourselves. Like I said, we have no reason to do this math for ourselves, so we use MATLAB instead, because otherwise it would take us years and probably reams of paper to do so. First, we define a chord length 5. Then we take the NACA number, which is a string, and convert it to a set of variables that we can work with. We then have MATLAB do the math, which I did on the whiteboard earlier, and then we divide up our surface into segments so we can calculate the coordinates of the airfoil surface section by section. We also create arrays full of zeros for our for loop, so when we define the values element by element, we don't get an error for trying to redefine elements that don't exist. The fact that there's zeros is arbitrary. We just need a template array full of some values. Next, we need a for loop. Here we have the loop setup. This loop will run 100 times because that's how many segments we defined with the variable n just earlier. We then calculate the variables xc, which is our x coordinate, divided by the number of segments, and yt, which is half the maximum thickness, which will both be used throughout our calculations. We then use an if statement to calculate the distance and slope before and after the line of maximum camber, which is p times c. The first equation is only for before the line of maximum camber. So we use an if statement to calculate for the distance and slope of each segment within the bounds 0 to p times c. An else statement is then used for the remainder of the y values and slopes. We then calculate the values of theta, which is just arctan of all of the slopes we just calculated, and then we can use theta to calculate the upper and lower surface coordinates of the airfoil, successfully decoding our NACA number into a series of useful coordinates. We then can plot it real quick so we can see what the shape looks like. It spits out some graph which looks like this. Now we can take these coordinates and actually make them useful. So we format the arrays of coordinates and put them into a file. More specifically, an SCR file, a script file which looks like this. We then open it up with AutoCAD. We use script to open our SRC file, then we use SplinedIt to convert it to a polyline, and then we export to a DWG file. So we have the shape of an airfoil in a DWG file, but we need to use a CNC router to actually make the final product. What's a CNC router though? A CNC router is a router, a tool that uses a spinning bit to cut shapes, usually in the edges of wood. But the key word is CNC, or computer numerical control. This means we replace those pesky, imprecise hands with motors and tracks to move the bit along the X, Y, and Z axes. We have 3 axes, so we need a 3D path for the tool to follow, also known as a tool path. And a DWG file isn't that, so we have to use another program, vcarve. We import our DWG file from earlier into vcarve, we set the cut depth, and let the computer know what end mill we are using. It then calculates a tool path and generates a CRV file that the CNC router can understand. We then use that CRV file in the CNC router and it does its thing. This leaves us with a carved block that just needs some finishing touches. So we use a laser engraving machine to precisely burn the CUA logo and name, as well as the NACA number, into the wood. This machine is controlled by a computer, which is software that is basically the laser version of a CNC router. We use some light sanding to remove cutting artifacts from the end mill. And then we are left with a finished product. The design process requires skills in many areas. Learning programs such as AutoCAD, vcarve, and coding languages like MATLAB can help turn concepts into tangible products that can be iterated on and shown to the world.